Welcome to solverfy.
Once again, welcome to a new problem. This time we kind of given a before and after scenario. So this is at a traffic stop. So think about a traffic stop, and there's a car standing right there, and you happen to be a witness. This is car B. Car B has a mass of um, 1900 kilograms. So the mass of car B is 1900 kilograms, and then it's standing. There's another car coming towards it, car A. This is before. The mass of A happens to be 1500 kilograms. Uh, Towards the right is positive x direction, and so the we don't know what the initial velocity of A is. We do know that the initial velocity of B is 0 meters per second because it's not moving. And then afterwards, so this is the after scenario, the two cars collide with each other. So there's a collision that takes place. Um, the two cars, at the intersection, they collide with each other. And so, after the collision, it happens like, somewhere right here, they collide, and then they stick together and they move a certain distance. Okay, so the distance is given, we're going to call it, this distance right here that they move, we're going to call it D. So that distance, we're going to call it D. And so D happens to be equal to, we're given that as 7.15 meters. That's the distance they're going to move. There's friction right there, and the coefficient of friction happens to be given as 0.65. Okay, that's the coefficient of friction in that case. So they're going to move up until they stop. So their final velocity, which we're going to call V final, of A and B together, they're going to stop. So it's 0 meters per second. So that's the information we're given at that point. In part A, we want to find the initial velocity of A before collision. The initial velocity of A before collision. And then in part B, we're told that the speed limit is 35 miles per hour. And we want to check if we want to compare the initial velocity, whether or not it's greater than 35 miles per hour or it's less than 35 miles per hour. This is just the speed limit. Okay, that's the speed limit. So again, we're going to use, on the next page, we're going to use the law of, not the law, but the work energy theorem. Work energy theorem, which says that the work done by friction equals to the change in kinetic energy of the system. That's what we're looking for. And so the work done by friction is the same as the change in kinetic energy. So, first of all, we have to think about the frictional force, or rather, the work done by friction would be Fk, so work friction. So we're saying Wf equals to change in kinetic energy of the system. Work done by friction is frictional force times K, which is mu K times the weight or the mass of the two cars, because they stick together, times the distance, and that has to equal to the change in kinetic energy, which is the final, okay, the final of A and B. Remember, the final of A and B is going to be 0, so we have to remember that. So if we go back to this, the final of A and B, that's it comes to a stop. So they move up until they come to a stop, and then this is minus the initial kinetic energy, which is pretty much the kinetic energy of both the moving car and the second car. The moving car and the second car. So 1/2 ma plus mb, and the initial velocity of the system. And the initial velocity of the system. So this one we have to change it a little bit, because they didn't stick together yet. So they didn't stick together yet. So that means we have to assume that we had the initial for A, the initial for car A, that's the initial velocity of A squared. This is squared, remember that. Plus the initial kinetic energy for B. And this one is squared too. Okay. So then you can see that if you go back, the initial velocity for B is 0. So that means this part will just be 0. And it helps us determine, this equation will help us determine the initial velocity of A, and that's our goal. And so this one becomes mu K ma plus mb times d, and then 1/2 minus this one also, this one, the combined final velocity is 0. So this one is going to be 0 too. So we're left with the minus here, minus ma va initial squared. So notice this part is 0 and that part is 0. So we're only left with this single part right here. And then we could divide both sides by we could divide both sides by uh, this is the initial for B. I think we have to change this a little bit, just a little bit. We'll have to go back a little bit. Yes, we have to go back a little bit, because we're dealing with the initial. Yes, so let's backtrack just a little bit. And that has to do with the right there. So this is minus ma times plus mb, And the final velocity, um, yeah, the initial velocity before they stop. So v, uh, I need some space on this. So this is v, a, and b initial. Okay, so that's what we're looking for. Remember, this one is 0, and so you end up having mu k ma plus mb times d minus 1 half ma plus mb. This one is squared, and then v ab. So that's the combined initial velocity just when they collide with each other, squared. We can divide both sides by ma plus mb because it's common, plus mb. And then we could also multiply both sides by 1 half. We can multiply both sides by 1 half, just to make sure our numbers are right. Remember, the frictional force is opposes the motion, so it's going to be a minus here, it's going to be a minus there, and then we could divide both sides by negative 1 half also. Okay, we could divide both sides by negative 1 half and this side by negative 1 half. So now we have a clean problem. This 2 will come up, the minuses cancel out. So we end up having VA plus B initial. So we'll do that in the next page. So VA plus B initial squared becomes the same as mu KD. Okay, mu K GD. Don't forget uh, the gravity. So there's a G right there, and there's a G right there. So don't forget that. Okay, let's just make sure. Yes. So mu KGD, and so we can use algebra to simplify to get the velocity just after they collide. So this is square root of mu K GD, and plug in the numbers. Mu K is 0.65 times 9.8 meters per second squared times the distance, which is 7.1 meters, and that's going to give us that velocity as 9.54 meters per second. And that's just the velocity just when they uh, collide with each other. Okay, then in the next page, we're going to use the law of conservation of momentum. We're going to use the law of conservation of momentum, which says that momentum before collision equals to the initial momentum before collision equals to the final momentum after collision. Before collision, we have ma and initial velocity of a plus mb and initial velocity of b. Just so you can recall, the initial velocity of b is 0, so that means this is just going to be 0. And then we have the second part, which says ma when they stick together and mb times the velocity when they stick together, which is va plus b initial, like that. And so our target is to get the initial velocity of a. We have mass of a plus mass of b times the combined initial velocity before they stop. This is I, like that, and that's I. Or you can actually have it outside. I think that's easier, like that, I. And then over the mass of A, we plug in the numbers. We get 1,500 kilograms plus 1,900 kilograms. times 9.54 meters per second. All of mass of A is 1500 kilograms. Just to go back and verify, you see the mass of A is 1500. So that's what we're using. And so the initial velocity of A as part A, the initial velocity of A happens to be 21.6 meters per second. So we want to see if it's within the speed limit. We're going to do that on the next page. We are given the speed limit as 35 miles per hour. So we'll multiply that by, we want to change that to meters per second. So 609 times 10 to the 3 meters of 3,600 seconds. And that gives us 15.64 meters per second. And you can see our speed of 21, our speed of 21.6 meters per second is greater than 15.64 meters per second. So it's over the speed limit of a speed limit by approximately 6 meters per second. Hope you enjoyed the problem. Two parts to the problem. The first part is before collision, and then you have after collision. We use the work energy theorem to determine the, on one side we have the frictional force which opposes the motion, so we have it as negative. And then we have the change in kinetic energy of the system, the combined system when they collide, the final kinetic energy, which is going to be zero when they stick together, and then the initial kinetic energy just when they collide with each other. That helps us compute the initial velocity of the two cars A and B when they stick together. And then we're going to use that with the law of conservation of momentum to find the initial velocity of A, which happens to be 21.6 meters per second. As you can see, we check if it's over or below the speed limit. Hope you enjoy the problem. Looking forward to seeing you in the next problem, and have a wonderful day. Okay, thanks. Bye.